Yeah. So, welcome to week 7 of the problem solving session. I am Mochandra Paul. So, a brief introduction about myself for those who are joining for the first time. I'm a PhD scholar in the Department of Chemical Engineering, and I'm working in the field of tissue engineering. And I myself has worked with various types of biomaterials for fabricating scaffolds using various biofabrication techniques. So, you guys, if you want to know more about my research, you guys can go and visit my website. Else, I'm I'll feel very happy if you ask questions. Other than that, if you have additional queries to this course, you can reach out to me directly through these problem solving sessions, or you can post it in the course forum. So, like this, we have been meeting since 27 Jan, every Saturday, 4 to 6 p.m. This is week 7. Next week will be the last session. All right. And also, I regularly upload the recordings of these sessions. So, if anyone wants to revise any concept again, so they can definitely do that through my recordings. And yes, I do take note of how many people are joining in these sessions. So in the interface that you have joined, the meeting interface, you won't be able to see any chat option. So if you have any queries, the best thing would be to unmute yourself and ask directly. Okay, I won't mind at all. Okay, and if you you can also raise your hand, so that option is also available to you. In that way, also you can communicate. So in this week, will like in today's session also, we will like revise about the polymers, synthetic ones, the natural ones, the hydrogels, and we'll solve few related problems. And towards the end of the session, I'll also briefly discuss the solutions to last week's assignment problems. All right. So feel free to ask queries in between, and if any other thing that you want me to discuss which is not there or I have not taken up, you guys can definitely like raise that information. Okay, I'll be happy to discuss that as well. So what are polymers? So polymers are nothing but long chain molecules. Doesn't have to be linear structure, but it can be of various structures, and they're made up of repeating units, which are called monomers. This is the main thing to know. Monomers together combine, and like they are covalently bond together and form polymers. So depending on how many monomers are present, you can have polymers of various molecular weights. And the reaction through which the monomers like covalently link together, that reaction specifically is called polymerization reaction. Now, if you were to classify the polymers, we can do so in multiple ways. One way is to use the property of the polymer itself. So I'm talking about the classification of thermoplastics, thermosets, and elastomers. Thermoplastics are those polymers which upon heating becomes quite soft. All right. You can like in that heated condition, you can deform it very well. But once it cools down, it will regain its solid structure. It won't be as soft. So their structure, the are objects made up of thermoplastics. Their structure can be changed by heating only. Whereas whatever thing you made out of thermoset polymers, this is another class of polymers, thermosets. Those structures, their shape is set. Once it is heated and poured into some mold and cooled down, that particular structure it remains. You cannot change it again or reverse the shape again by heating. So those are thermoset polymers. So thermoplastics, example like polyethylene, whereas thermosets is the polyester resins. So polyester resins, they are usually very transparent, very transparent. Like you must have seen coasters made out of it, or any type of fancy earrings or something like that of these, or even the keychains are made up of polyester resins. So if you try to melt it, even at very high temperature, it will like the structure will not uh, like become very soft. Then by nature, the hard solidified structure is very hard and brittle, whereas thermoplastics, they can be made into a deformed is very easily. That is why they are kind of ductile in nature. Okay. And there is a third type of polymers, that are elastomers, example being the silicone. So these elastomers, they can be very flexible in nature, even without heating. Okay. So these are the three classes of polymers based on the uh, native property. Now, based on the source from where these polymers are derived, we can again classify into natural and synthetic. The natural polymers, as the name suggests, from the nature. So we take it from the plant, animal, microbes. Okay. So we can again classify natural polymers based on the chemical structure, based on its chemical structure. So if the structure contains mainly the sugar components like glucose or similar molecules like glucose, then those are polysaccharides made up of saccharides or sugar components. Whereas another type of natural polymer is called proteins. So here they are made up of mainly amino acid kind of molecules and a peptide bond, that is NHCO. This peptide bond can also be seen in these polymers. Okay, so we will like in detail we will see the natural polymers and understand more about their properties in the later slides. Now the polymers, they are very widely used in almost every sector of engineering. Okay, uh, if when it comes to biomedical application, we can list down, and the application that I've given here, these are only few, but there can be many more. So we can use polymers to make surgical devices, implants, drug delivery systems, biosensors, dental materials, orthopedic materials like orthopedic implants and all. You can use polymers in those applications. And lastly, for tissue engineering applications, to create artificial tissue structures. Okay. Now, how to synthesize, how these polymers are synthesized. So two main mechanisms of synthesis include addition polymerization reaction. It is also called chain reaction, where a free radical is needed. So these free radicals, it contains an free electron, all right, and they are very reactive in nature. So these free radicals are added to initiate the polymerization reaction, and then these free radicals go and react with a stable monomer, and it makes that monomer in turns that monomer into a free radical form, and then like in this way the creation of free radicals propagates. Ultimately what happens when large amount of free radicals are created, they kind of bond together, okay, and form stable groups, maybe two monomers or three monomers or four monomers. They will form one particular molecule. Okay, so in this way, the reaction at the end terminates. This is a chain reaction. Why chain reaction? Because free radicals, they are like targeting one molecule after the another in like sequentially. Hence the name chain reaction. Whereas for condensation polymers, we see that two monomers doesn't have to be the same type of monomer. They react with each other and releases a simple molecule. Okay, as a like that simple molecule is basically a byproduct of that particular reaction. So it can be a water molecule or a ethanol or methanol molecule. Okay, so they condense and form one single molecule. So various polymers. So and if we were to increase the length of this polymer chain, so two molecules in one step form one, the product is one molecule, and in the next step another monomer will come and condense, or the condensation reaction will happen between the ends of the product of the first reaction and the new monomer. So in this way, in every set of reactions, in how many are required, s- a simple byproduct like water molecule or ethanol or whatever, that will be released. And the removal of these byproducts is relatively very easy. If it is water, we can simply evaporate it. Okay, if it is ethanol, methanol, they are volatile, so again evaporation will work. Or they are they are like of lower molecular weight, so they will come up, they will phase separate. So in this way, stepwise, in one step, a product of two monomers will form, then another step 3, another step 4. In this way, stepwise growth of the polymer chain takes place in condensation polymerization reaction. So in either, using either of these synthesis mechanism, one can try to synthesize these polymers. Now, polymers can be found of containing various type of architecture. So you can have a polymer where which consists of only linear chains, but there are no side chains. It is like one only. It consists of only a linear architecture like this. Okay, there are no side chains or pendant groups hanging above or below the plane of this linear molecule. Then if such pendant groups exist or some subsequent groups exist, then they exist and create a branched kind of architecture like this. Okay, so this is a branch architecture. Now it is possible that multiple type of polymers, multiple polymer chains, basically they can come close to each other, and the substituent groups, they can covalently or physically, means either chemically or physically, they can bind to each other. So that is called cross-linking. So if that cross-linking is happening, then you get a cross-linked architecture. So so this is a branched. So how cross-link architecture will look like? This is a backbone of a polymer chain, and from the backbone you will see some pendant groups hanging. Now, these pendant groups will have some functional groups, suppose, that can go and bind with the functional groups hanging out from another polymer chain. And in this way, these crosslinks get created. So these crosslinks can be chemically crosslinked, means some covalent bond is formed, or they can be physical crosslinks as well. Even if the branched architecture is not there, all right, physical cross-linking can happen in presence of some ions or due to some electrostatic bonding or due to some hydrogen bonding. So that can also give rise to a cross-linked architecture. Now, when various polymer groups, they are cross-linking above and below the plane, okay, and creating a network structure like a woven mat. How the uh, jute fibers, they are woven together, right, to create a maybe a jute bag. Similarly, these polymer chains, they can have groups, all right, which are cross-linking with another polymer chains, and they are like going above and beyond, like above plane, below the plane, and creating a network structure. Now that is another type of architecture which we can find in polymers. So these are four types of architectures of polymers. Now, depending on the monomers, what type of monomers are there and how they are arranged, we can classify the polymers as homopolymers where there is only one type of monomer. Okay, or there can be two types of monomers, then they are called copolymers, like A, right? So B is like another monomer type. Now, the arrangement of this A and B monomer can vary. So they can be like randomly placed in the polymer chain. Okay. Or they can be like in alternating fashion, like A, B, A, B, A, B. Or they can be in block form. So what is block form? So the tendency is there that 3 units of A will come first, then 3 units of or 4 units of B will come later. In this way, this is a block of B, this is a block of A. So in this way, block copolymers can be formed, or random copolymers or alternating copolymers can be formed. Next, we can classify the polymer based on their tacticity. So tacticity refers to the arrangement of the substituent groups that are hanging away from the backbone of the polymer, that backbone that is the polymer chain. So how the substituent groups are arranged around the backbone. So depending on their arrangement, we can classify the polymers as isotactic, means if let me just clear the pen markings. So yeah, isotactic means if this is the backbone, suppose, all right, and all the substituent groups, they are coming out towards one side, are present on the one plane only, and that is called isotactic. Then it is also possible that these substituent groups, they are present in alternating fashion. I mean, one substituent group is above the plane, another substituent group is below the plane. Okay, so that is symbiotic, alternating arrangement of this substituent group around the linear polymer chain or bone. Or it can be in random way, like the placement of the substituent group has no pattern. Basically, they are randomly placed. That is atactic. The tacticity in that case will be called atactic. So and it is seen that polymers which are having atactic type of tacticity, their nature is more amorphous. Okay, they means amorphous means like very irregular pattern, right? That is amorphous, the basic understanding, like what we understand from amorphous, it means like something, the structure is very random, there is no pattern, inherent pattern present in it. So if the polymer having atactic type of arrangement, then the polymer will most likely be of amorphous type. Whereas if the polymer is isotactic or syndotactic, then maybe the polymer will be of crystalline form. Now, polymers can never be pure crystalline like metals. Some part of the polymer can be crystalline and some part can be amorphous. So a polymer cannot be pure crystalline. That is why those polymers which have some degree of, or majority of the part is crystalline, then we call them semi-crystalline. So these semi-crystalline polymers can be formed if the tacticity is isotactic or syndotactic, means the arrangement of the substituent group is either on only one plane or in alternating fashion. Then the polymer can be categorized or can have the property of crystallinity, means it can be called as crystalline polymer or semi-crystalline polymer. All right. Now, um, also a polymer cannot have one molecular weight, one single molecular weight. Okay. Why? Because the number of repeating units, it affects the molecular weight of the polymer. The larger the number of repeating units, the larger will be its molecular weight. So we can calculate the molecular weight based on this number, okay, n, that is called number average molecular weight, or we can calculate based on their weights of these repeating units, okay. So that is called weight average molecular weight. People also calculate the molecular weight based on the viscosity. That is called viscous average molecular weight, but that is not discussed here, okay. So we have here another TA, Mr. Karthik. So if you have any queries, then also Karthik can help you guys. Okay. So as I was saying, that number average molecular weight and weight average molecular weight, they are slightly different from each other. So number average molecular weight are calculated in this manner, where Ni, okay, Ni is the uh, number of the polymer chains, okay, and each polymer chain will have some molecular weight associated with it. And then this will, depending on how many number of polymer chains of different molecular weight are present, we calculate the number average molecular weight. Similarly, the weight, individual weight of those polymer chain in a mixture, okay, and we use those weights to calculate the weight average molecular weight. Again, the viscous average molecular weight is not discussed here. Always the weight average molecular weight is greater than number of average molecular weight. So these two things to be kept in mind. Then the degree of polymerization. So what is degree of polymerization means how many repeating units are present basically. So you have already done a problem like this where the entire number average molecular weight is given to you, and you know the molecular weight of the monomer, and you have to find the number of repeating units. So that is actually you are calculating the degree of polymerization. And this is the similar formula you have used in that particular question. Then using the weight average molecular weight MW and MN, number average molecular weight, you can calculate the PI index, also called the dis PI index. So uh, PI index stands for polydispersity index basically, and it denotes how heterogeneous your polymer mixture is. So if it is close to 1, if the value is close to 1, then we assume that your polymer mixture has polymer chains all of similar molecular weights. Okay, but that is rarely the case. We usually have PI index greater than 1, like 1.2, 1.5, similar. Okay, now depending on the structure, again the architecture of the polymer, like we discussed previously, the linear architecture, branched, crosslink, and network architecture, we can suggest how much will be the strength of our polymer. So here is the order of strength given here. Network polymers, they are having a higher strength in comparison to the linear polymers. You can understand why, correct? So cross-linking or the network architecture, they bind the polymer chains more closely, which in them much more strength when compared to the branched or the linear type of polymers. Also, higher the molecular weight or higher the degree of crystallinity observed in those polymers, higher will be its strength. So higher molecular weight means the chains, polymer chains, they have groups which are more bulkier, or in inversely you can say that more number of polymer chains are there, right? So molecular weight has increased. If the crystallinity is high, means the isotacticity is more, then also the strength can increase. Now, again, based on thermal properties of the polymers. So it becomes important when you are using polymers for like for heating or for biofabrication applications where you need the polymers to heat up and transition its state from liquid or solid structure, and you want to understand that particular temperature when the transition is happening. So in that case we see what is the glass transition temperature and what is the melting point, or tm values. So for, if the polymer is having more of an amorphous nature, then the importance of Tg becomes much more higher. Okay. Whereas for semi-crystalline polymers, uh, Tg will be there, all right, but Tm, considering the Tm part, also becomes very important. So Tg suggests that temperature at which the polymer changes its state from a glassy state, which is a much more hard and brittle state, to a rubbery state, which is a flexible state. Okay, so that is a Tg value. Whereas if the polymer also has a crystalline nature associated to it, then we can see that at higher temperature, Tm is usually greater. Tm is usually greater than Tg. So at this higher temperature, the polymer can transition directly to liquid state. Okay, and it can be used like for any biofabrication application. Okay, now you can use two or more polymers together, and we make something called polymer blends. So we make polymer blends to get desired property. So one polymer is not giving the needed property for your application, so you mix two of them. So and these two polymers doesn't necessarily have to bind together through covalent bonds. There can be physical bonds as well. Only the mixture should be stable with itself. There should not be phase separation. Sorry, should not be phase separating from one another. Then you won't be able to get any new property, and the polymer blend will not be formed correctly. Okay, so we will solve few problems on these polymer blends as well. Now, what are composites? So composites are formed when you are combining two or more different materials. So polymer blends, you are making a mixture of two or more polymers, whereas in composites, you are mixing or combining two or more different types of materials, like ceramics and polymers, polymers and metals. And the beauty of these composites is like you can actually understand where the ceramic ends and where the polymer ends. Means there is a clear uh, line. Okay, whereas in polymer blends it's very difficult to separate the two components out from one another if the blend has perfectly mixed with each other. Whereas in composites you can definitely understand like this is your ceramic part, this is your polymer part. So in this way also the properties of the composite, it becomes completely different from that of the individual components, and we do it for a particular application. Okay. Now, here's a very, so if you have any queries related to anything that I've discussed in last few slides, please let me know. Any queries? So I tried to summarize like everything that was taught by Professor Doble in his lectures in 4 or 5 slides to just to summarize everything. So in that, if you have any queries, let me know. Okay. So moving forward, here's a small question in front of you. So which of the following are FDA approved polymers? Is this question visible on your screen?
Visible.
Visible, no? Or not? Is it visible now? So the question says, which of the following are FDA approved polymers? So I have drawn four polymers, and also there is a fifth option, all of the above. So maybe a guess from any one of you to answer which of these are FDA approved polymers. So you know FDA, right? Food and Drug Administration. So they have to they do various safety and efficacy tests on these polymers and make sure that the use of the polymer on humans is safe and it is happening ethically, and all the regulatory guidelines are being followed. So they make those guidelines, and we who are going to use it have to follow those guidelines and then make our product using their approved polymers. So anyone would like to guess which of these are FDA approved polymers? Anyone? So is PLA a FDA approved polymer? What do you think? PLA is widely used for various applications. Do you think FDA has approved it for its use on human? Yes, no? Don't worry if you are wrong.
Yes.
Yes, okay. So PLA, what about PCL then? Is it FDA approved? PCL stands for polycaprolactone. It's a polyester. Okay. Yes, no, maybe no, because you guys are not answering. What about PVA? Polyvinyl alcohol. Is it a FDA approved drug? Sorry, polymer?
Yes, no.
Yes. What about PLGA? Polylactic glycolic acid.
Yes.
Yes. So PCL, any answer? Yes, no for PCL. Is it FDA approved? So actually the correct answer is all of these are FDA. All of these, PLA, PCL, PVA, PLGA, which is why if we are talking about translational research, means whatever research we are doing in a lab and we want to directly use it on humans, then the safest choice of the polymer would be these polymers, which are already approved by FDA. And then it will become much more easier, and the process of translation will be much more faster. So yeah, maybe something to note if any one of you would like to do research in this area. Now, which of the two uh, is a hydrogel? Here it will be which of the two. Okay. So which of the two is a hydrogel? So it is a structure of PMMA and this is a structure of polyhema. So which of these two structures do you think is a structure of a hydrogel? So this part is same in both of them. So how would you recognize from the structure that it's a hydrogel or it can be a hydrogel? Maybe a guess that it's a hydrogel. As the second part of the question is how. That is why I want you guys to look at these structures carefully and try to understand. One of them is a hydrogel, that's for sure, but how it can be a hydrogel?
Maybe with OH group, which may be stable, and H1, which is more reactive, like something like.
Yes. So this OH group in polymer, it can contribute to hydrogen bonding with water, right? And you know the inherent property of hydrogen, they can absorb and retain a large amount of water. So this OH group, through hydrogen bonding, can allow this retention of water molecule, and that is why this is a hydrogen, whereas PMMA is not a hydrogen. So directly from the structure, you can guess which is a hydrogen. Okay. Now here's a simple math problem based on polymer blends. The question says that there are two polymers, PET and PLGA. PET has elastic modulus 3.5 gigapascal, whereas PLGA has 1.5 gigapascal. And they are mixed together in 1:1 ratio or 50:50 and prepared a polymer blend. Now we have to find first the Young's modulus of this blend. So we will be using the mixture rule to do that. So suppose E denotes the Young's modulus of the blend. We can find it using simple expression E PET into volume fraction of PET plus E PLGA into volume fraction of PLGA. So this is a mixture rule. And V, they are volume fraction, not volumes. Please note, these denote volume fractions. So we have the values of the elastic modulus, as well as we know that these polymers are mixed in 1:1 ratio. So we have the volume fractions as well. So directly add these values. So 3.5 gigapascal into zero point 0.5 plus, here the Young's modulus of PLGA is 1.2 into 0 0.5. So if you guys have a calculator, uh, put these values in your phone or any calculator and let me know what you get. Are you doing it? If one of you have done it, let me know the value.
1.99.
Sorry, can you repeat?
1.99.
1.99. So approx 2 you're getting, no?
Yeah.
Okay. Anyone else getting anything different from this?
2.35.
2.35. Okay. It's very similar actually. Anyone else? Okay. So I think like whatever answer you will be getting will be very similar to 2 or 2.3. Okay. So depending on what type of calculator you're using. So the correct answer for A is, like, the value I got was 2.35. Okay. Now for part B, Mm. So, for part B, we have to calculate the percent load borne by PET when the blend is subjected to a load. Means how much load is or can the PET of this blend can uh, take upon itself. So how will you do it? For that, just consider that L. So L denote the load, and we are focusing on PET. The load borne by PET is denoted by LPET, and percent we have to find. So first take a fraction and first find the fractional value, and then you can multiply with 100. So it will be, so this is the fraction we are going to calculate. Load borne by PET divided by total load borne by this polymer blend. So also load, you know, is directly proportional to your elastic modulus. Correct? Elastic modulus is equals to stress. Stress is load by strain. So there is a proportionality. So for doing this calculation, just consider the value of elastic modulus that you already have with you. Okay. So you know 0.5 or 50% of the blend is PET, and it has a elastic modulus of 3.5 gigapascal. And what is the total load? So you take that value that you calculated just now, or you can write it in this way. So this value is basically you have calculated the denominator part you have calculated in part A was 2.35. Now if you do this calculation, someone do it and let me know the value. This value will give you the uh, fractional uh, value, and then you can take a percent, and that percent is your answer. Someone do this calculation. So what have you found?
0.74.
0.74. And if you take a percent, it is close to 74%. So that is a like correct. Okay. And now the C part. What is C part? It is saying that after 10 days, half of the PET and one third of PLGA has degraded. Now, what will be the Young's modulus of this blend? So, if you write the problem now like this, at T0, PET consisted of 50% of the total volume, whereas PLGA consisted of next other 50%. Now, after 10 days, T is equals to 10 days, you found what? You found half of the PET is gone. So remaining half is left. So after so after 10 days, PET is 25%. So 50% ka half, 25% is left with you. Whereas PLGA, how much PLGA is degraded? One third is degraded. So how much is remaining? Two third is remaining. So 50% ka two third, if you do, you will get something around 33.33%. Now this is your current volume fractions of PET and PEGA, sorry, PET and PLGA. Now, using these volume fractions, you have to calculate the elastic modulus using the mixture rule. So, use the mixture rule to calculate the elastic modulus after 10 days. So, it will be 0.25 for PET. I'm writing first 0.25, 3.5 into 3.5 gigapascal plus 0.33. Wait, I think I did something wrong. We have to calculate the volume fractions, new volume fractions now. If you see, these two are not like, we cannot use them directly. So first we have to calculate the volume fractions. Sorry. So in total, so in here we could have directly written V2 plus V1 is equals to 1. But now this after 10 days, it is not equals to 1. So we have to find the values, find the values of volume fractions separately, so that we will get, whole, so that we can add them and get one value. I hope you're getting what I'm saying. So if you do that, you get the volume fraction of PET. Similarly, we'll get volume fraction of PLGM. Now we have to use these current or calculated volume fractions to calculate the new Young's modulus. So if you put these values into calculator and find, then I got a volume fraction of 0.428 for PET, around 43%, and for PLG I got 5.571, so around 57%. Now these two will add up to 1, correct? That is the definition of what that is what we were trying to do or have been doing. So these are the volume fractions. Now we have to use these to calculate the Young's modulus of this current blend after 10 days. So it will be 0.428 into 3.5 plus 0.571 into 1.2. This is for the PLGA. This part is for PET. Now tell me how much the value you are getting for this equation. Are you guys getting it? Are you guys following along? So what is the value of E you are getting now?
2.098, ma'am.
2.098, approximately 2.1. Okay, anyone else getting anything different? I think this is correct. Let me check. So yeah, 2.18. So yeah, 2.1, 2.2. Either of those answers will work. So if someone is getting similar to this value, you are on the right track. Okay. So have you understood now how this type of problem is solved? What we did, we used the mixture rule to calculate the Young's modulus of this blend first. Then we were asked to calculate if some load is given to this polymer blend, then how much of this total load will be experienced by PET. And similarly, we can find the how much load is experienced by PLGA. So for that, what we did, we took a ratio of the basically the elastic moduluses that we got. So we know 50% of the blend is PET, and so how much load will be uh, can be experienced by this PET content? So it will be 50% or 0.5 into 3.5. This will be the numerator divided by the total polymer, how much it will experience load. And we are using the values for elastic modulus only, because elastic modulus is directly proportional to the load or vice versa. Load is directly proportional to elastic modulus. So in this way, we are calculating 74% of the polymer uh, can experience like 74% of the load is experienced by PET, and rest remaining load is experienced by PLGA. So that makes sense, right? PET has a very high elastic modulus, so it can definitely bear much more load. And C part, we were told that uh, some part or half of the PET was degraded, and whereas one third of the PLG was degraded. Now the remaining polymer blend content, we have to, for that remaining part, we have to determine the elastic modulus. So first we have to find the new values of volume fractions. So the new values of volume fractions in this polymer blend, and using these new values of volume fractions, we have to calculate the elastic modulus for part C. Now if you note, the values of elastic modulus after degradation has decreased. It is lesser than the initial one. It was initially we got 2.35 gigapascal, but now it has reduced to 2.1 gigapascal. So it has happened due to degradation. So this type of logical reasoning you can do with yourself when you are calculating such type of problems on your own. Now there's another problem. Now this problem is based on composites. So we are given basically fiber reinforced PMMA. Some fiber is there and it is reinforced or or inserted within the bulk, or is present inside the bulk of PMMA polymer. And this particular composite is used to prepare a tubular implant. So and we are also given the individual elastic modulus values of the fiber. So fiber has elastic modulus of 200 gigapascal. PMMA has an elastic modulus of 5 gigapascal. Now, in order to achieve 145 gigapascal modulus, how much fiber should be added? So we have to calculate the volume fraction of the fiber that we must add into this polymer so that the final elastic modulus is 145 gigapascal. So for this question, let me just add a blank slide first. Wait a sec. Sorry for the interruption. So I just added a blank slide into this PPT so that I can show you the workout nicely. So for part A, I have to use the mixture rule, but in a slightly different fashion. The logic and all remains the same. So we are given the final elastic modulus, that is 145 gigapascal. This is the final elastic modulus of the composite. How did we find? So we have to use the elastic modulus of PMMA and the volume fraction of PMMA. So we don't know the values yet. We only know the value of elastic modulus of PMMA. Plus, that is the fiber. Elastic modulus of fiber is given, and the volume fraction of fiber. This is just writing. I've just written here the mixture rule. So these elastic modulus values we know. And we also know volume fraction of PMMA and the volume fraction of fiber. If we add them up, then it will sum to value of 1. What? It will sum to a value of 1. Now, use this. So, this value will be one minus V fiber plus 5 into V fiber. If we simplify this, we can find the volume fraction of fiber. That is what we have to actually find. What should be the volume fraction? So it will, if we like simply rearrange it, okay. So I'm not doing the complete rearrangement. I'm just writing the final ratio. It will come out to be 140 by 195. So you just have to, 200 minus 200 minus 5 would be there. 200 is the volume elastic modulus of fiber. Sorry, some mistake from my side. Sorry, let me rewrite this expression again. Fiber has the elastic modulus of 200, not PMMA. So 200 into fiber. And 5 gigapascal is the elastic modulus of PMMA. And as I told you, that volume fractions add up to 1. So we substituted volume fraction of PMMA with 1 minus V fiber. Okay, I think it should be understood now. Let me just write the simplified form. Now, I think V fiber will be equal to 140 divided by 195. Yeah, now this is correct. Sorry. So if we take the value here, if we take the ratio of 140 by 195, and what I got was 0.72%. Take a minute to do it yourself and let me know if you also got 0.72. Did you also get 0.72 or 72% is the answer here? So we have to add 72% of the total volume fiber in order to get total elastic modulus of 145. Have you guys understood it? Yes, no, not interested anymore. What is it? You can say if I'm teaching very boring way. It's totally fine.
Mm, 0.717.
0.717. Yeah, it is coming to be 72% also. Okay. So now this is part A. I think you have understood part A. Now, how will you approach part B? So part B says that the cross-section area of the implant is 2 centimeter square and the fiber diameter is 15 microns. Now, how many fibers are required? So this is a composite. So this is and also this composite is used to make a tubular implant, which will look something like this. So inside the bulk, this small circle that I'm drawing, these are basically fibers. In this way, they are planning to reinforce it. So we have to just find out how many of these fibers are required inside this in order to fill this entire tubular implant. And to help us calculate, we are given with the cross-sectional area of the cross-sectional area of the tubular implant, that is 2 centimeters square, and the diameter of one fiber, that is 15 micron. So how will we start? So let me again write what was there in the question. Cross-sectional area of implant, 2 centimeters square. So what will be its volume then? Volume of implant. So usually it is cross-section area into length, some length. So let's call that length to be L. Okay, later on it will cancel out, so don't worry about finding the value of L. Now, what is the cross-sectional area of fiber? So it's again, I'm assuming that it's a tube. Fiber is like a tube or cylindrical geometry itself. So the cross-section is circular. That's why I'm considering pi r square, or in this case, pi d. So d is 15 micron by 2 square. This is micrometer square. So if we convert it to centimeter, I should have done it previously as. So it will come out to be -4. 15 into 10 raised to the power -4 whole square. This is centimeter square. So actually, uh, 1 micrometer is equals to 10 raised to the power -4 centimeter. You can cross check this if you want. So if you convert into centimeter, this is what you will get. Simplified, you will get 7.5 square into 10 to the power -8 centimeter square. This is the cross-sectional area of the fiber. Now, what will be its volume then? So length of the fiber will be same as the length of the implant. I hope you are getting why, because we have to completely cover up the entire implant. The fiber should be present throughout the bulk of the implant, which is why its length will be same as that of the implant. So L into the cross-sectional area value that we just obtained. Okay. Now we know that only one fiber won't be present, right? There will be some n number of fibers. So what will be the volume of n fibers then? It will be n into L into this value. Okay. Now what else we know? We know the volume fraction of the fiber. We know that 72% of the entire implant is having the fiber. So we can use that information here now. How? For- Uh, in this expression that I'm writing, I'm saying that the volume of the fiber that we got, n fibers that we got, just have a look at it, then I'll explain. Okay. So this is the expression. This is the final expression that will help you get the value of n. So what I did, we know the volume fraction of the fiber that is present in the bulk, that is 72%. And from the definition of volume fraction, we wrote this particular ratio. The numerator consists of the volume of the n fibers, denominator is the volume of the entire implant. And we have to calculate the value of n. So this L will cancel out, correct? And n will become 0.72 into 2 divided by 5 into 7.5 square into 10 to the power minus 8. So someone quickly calculate this value of n and let me know what you are getting. So what value are you getting?
Eight point one five into 10 to the power 5, ma'am.
Okay, 8.15 times to power 5. So anyone else getting anything different from this? Okay, I'm assuming that you guys are getting the same value. What's the answer? This is the answer. Okay, so you have obtained the correct value. This is the value of n. So we need almost 8 lakhs of these fibers to be reinforced. Now, here important assumption that they took was all the fibers are aligned in the same direction. Okay, that is the important assumption that we have to that we have considered basically while calculating this value. By the way, in realistic, if we see in real situation, it is not always the case. Okay. Now coming to the next topic, Briefly, I'll discuss the natural polymers and the hydrogels. Okay, briefly, very briefly. So natural polymers, they are derived from natural sources, that is from directly from nature, like the plants, the microorganisms, and the animals. Mainly two types of natural polymers are used for biomedical application. One is the polysaccharides and another is the protein. But there are other as well, like polyesters, polynucleotides and all. So those are also natural polymers. Then they are easily, if when we are using it for a biomedical application and trying to and when they get in contact with our body, then they can be easily recognized by our body. Okay, because they have some structures or domains inside them which are very similar to those which are present inside our body. The cells immediately doesn't find them foreign. The body accepts it, like somewhat accepts it, but there is not 100 degree of acceptance. That is why another thing is they can also give immunogenic responses, like they can have some immunogenicity. So one example of this is collagen. So collagen is a protein that is already found in our tissues, but for the biomedical application, we use collagen from animal sources, like say rat. Okay. Now rat and humans, they are both mammals, but there are differences, right, in the genetic level, which in turn gives some uh, differences in the structure of the collagen as well. So when these collagens are, if suppose are used on human, they will most definitely give some immunogenicity because of those minor difference in say amino acids or change in the domain site. So which is why immunogenicity also becomes a problem when you are using natural polymers. Then the way these natural polymers are extracted, they also add in some variability, batch to batch variability. And since they are taken from natural sources like animals, plants, and all, so the supply of these polymers becomes limited. We cannot just go one day in lab and synthesize it. So they have to be specifically extracted from the animal or plant tissue and then processed in such a way that makes it usable for our application. Most of the natural polymers are biodegradable, means they when they come in contact with biological enzymes like hydrolysis and all, they can easily degrade the covalent bonds present in it. The components or the natural polymers which are used, they're very much similar to those present in our ECM, tissues ECM, which is why in tissue engineering, we widely use natural polymers to make our artificial tissue much more mimicking to the natural ones. Cells very nicely adhere on these natural polymers. Okay, that is why we see more cell growth and a better performance of our natural tissue, of our artificial tissues. There are various examples like with the hyaluronic acid, chitin, then chitosan, alginate. So these are all some polysaccharides. When it comes to protein type of natural polymers, then there is gelatin, collagen, silk, fibrin. So these are all protein type of natural polymers. So that's it. Like rest of the information you will definitely get from the lectures. And I'll not go into much detail about each of these polymers. Now, let me briefly describe about the hydrogels. So are you guys able to see the hydrogel slide on the screen? Oh, I think. Yeah. So hydrogel slide is there. So hydrogels are a polymer form, you can say it is a form of polymer where the polymer chains, they form a 3D network structure. And these chains doesn't have to be chemically cross-linked. They can be physical cross-linked as well. So there can be physical bonds like hydrogen bonds, electrostatic bonds, ionic bonds, which hold these polymer chains with each other and form a network structure. Or you can covalently cross-link them using some covalent cross-linking agents and create a network structure. The unique property of this network structure is they can absorb and as well as retain large amount of water. Means there are various polymers which can retain water like 10x of their own weight. So various polymers are reported. Means when they are kept, when these hydrogen polymers are kept in water, like plain water, it will swell completely in volume. Okay, and then when they are dried, it will become like shrinked. So that is the beauty of hydrogels, and because of this particular property that they can retain a large amount of water, these hydrogels are widely used for tissue engineering applications because they can mimic the aqueous environment of our body and allow the cells to thrive in that environment and grow well. Okay, so how they are retaining this much amount of water? They are doing it because it contains various hydrophilic sites, OH groups, for example, like I showed you for polyhema. These hydrophilic sites, they can bind to water molecules through, say, hydrogen bond or electrostatic linkage or anything. Okay, so because of these domains, it is able to retain the water. Now, hydrogels, if you see the chemical structure, they can be having various kind of groups present in it. So based on your application and availability, you can choose any hydrogen material, and and all of them will show the same property that they will be able to absorb and retain large amount of water. But since the water content in the hydrogel is too high, it overall reduces their mechanical properties. Means they cannot bear large amount of load. Okay, so we have to again think in what application these hydrogels can be used, because they have poor mechanical properties. People have also started making something called smart hydrogels. Okay, these smart hydrogels have the ability to sense its environmental cues. So if there is a change in pH, the porosity in the hydrogel increases, because of which the flow of water molecule increases and it swells up. Whereas if the pH is changed back to its original condition, the swelling reduces. Similarly, there are temperature sensitive hydrogels, and then there will be other cues, just and even ionic based on the concentration of some ions in the environment, that also regulates the swelling and deswelling of these hydrogels. So these are called smart hydrogels, which are sensitive to various environmental cues. So you can use these hydrogels or the smart hydrogels for drug delivery purposes, where you want specifically to drug first deliver the drug and release the drug only at the target site. And if you know, say, your drug is supposed to target a cancer, and near the cancer there is pH is very less, it is acidic pH, means it is not 7.4 anymore. So you can design a hydrogel which can sense this acidic pH, and it will only swell up. The porosity of the hydrogel will only increase when it senses this lowered acidic pH. So in this way, you can target the delivery of that drug only to that acidic site, that is only to the cancer, not elsewhere in the body. So in this way, you can do targeted drug delivery using smart hydrogels. Now, based on various factors, we can classify them. I have mentioned 3 ways, but other ways of classification is also possible. So first way is whether the hydrogels are formed through chemical cross-linking or through physical cross-linking. So you can define as a chemical hydrogel or a physical hydrogel. Next, if the hydrogel is from a natural source or a synthetic source or hybrid, or also called semi-synthetic. So natural means directly from the nature, like plant, animal, microbe. Synthetic, you are preparing directly in the lab, or hybrid means you take it from the nature and then you do some modifications. You add some chemical groups and all, and make it hybrid, semi-synthetic. Now, another way of classifying hydrogels is whether the hydrogel consists of homopolymers, means all the repeating units are same, copolymers, two different or two or more repeating units are there, or multipolymers. Now, another interesting point to note is that a hydrogel consists of water in various states. Basically, there are three states of water that can be found near or bound to hydrogen. First is the free water. This free water is a bulk water. It behaves like bulk water. It is not directly bound, not bound to hydrogen. Whereas there is some water molecules which are weakly bound to the hydrogen. This is called freezing bound water. Whereas there are few water molecules which are very tightly bound to hydrogen network. So it is called non-freezing bound water. So, so the free water, it will behave just like the water we drink. It will freeze at 0 degrees Celsius. Whereas freezing bound water, which is like weakly bound, it has the ability to freeze below 0 degrees Celsius. So maybe minus 20, minus 14, 15, like that. Whereas the water molecule, which is very tightly bound to the hydrogel, it is bound, but it will not freeze even up till minus 70. So if you want to freeze this water, you have to use liquid nitrogen, which is minus 196. Then you will get a hydrogel where all the types of water, whether it is weakly bound or tightly bound or freely bound, so like freely available, all those water molecules will be frozen. And then you can use it for any application like freeze drying and all. Okay, so these are the three states of hydrogens that are found. So here's a simple question. You know hyaluronic acid, so it is a polysaccharide. It's a natural polymer, and it is also a hydrogen. But but the structure, if you have carefully listened to the lectures, sir has shown the structure of the hyaluronic acid to you. So if you, I don't know, remember the structure, if not, don't worry, I'll show you. So that structure has two types of molecules. It's a disaccharide. So one molecule is a glucuronic acid, another is called N-acetyl glucosamine. So they are linked together. I want you to answer which linkage is present between these two molecules. Just simple guess. If you don't remember the molecule structure, just simple guess. See, gamma linkage won't happen because there's like it is not known. Delta linkage won't happen. So either beta linkage or alpha linkage, either of these will be the answer. A simple guess would work. Anyone would like to try to answer this question? Hello, am I audible? Maybe simple Google it, the structure of, yes,
Beta linkage, ma'am.
beta linkage. Okay, so you're correct. So those of you who don't know the structure or didn't Google the structure of hyaluronic acid, so it looks something like this, which is I'm showing now in your slide. So this part is glu glucuronic acid. It is the C1 carbon of this particular acid. C1 is linked to third carbon of N-acetyl glucosamine. Okay, and why beta? Beta because this particular group, N-acetyl glucosamine, is present above the plane of this particular molecule. That is why beta linkage is there. Alpha linkage is there. When we call alpha linkage, when this particular ring, second molecule, is present below the first ring. Okay, and these linkages are usually made with respect to carbon 1, and this carbon 1 or first carbon is linked to any other carbon in the second molecule. Okay, and people have also seen that first carbon can link to 4 carbon. So this molecule is a disaccharide. This is a disaccharide. Sorry, I apologize for the spelling. So this disaccharide can then again bind to another glucuronic acid. Now in this case, there will be beta 1,4 linkage, and then again beta 1,3 linkage, then again beta 1,4 linkage. This way it continues, the linkage type continues, but the beta linkage exists. One there is 1 to 3 carbon, another way it is 1 to 4 carbon. And in this way, the structure of hyaluronic acid is completed. The correct answer is beta linkage. Now, if equilibrium swelling is lower in basic than acidic condition, then it is what? A cationic. So here, this question is based on hydrogels. Please note, this question is based on hydrogels. So for a hydrogel, if the equilibrium swelling is lower in basic condition than in acidic condition, then it will be what? Whether it will be a cationic hydrogel, an ionic hydrogel, non-ionic hydrogel, polyionic hydrogel. Anyone? Give it a guess. You have a hydrogel which uh, swells, all right, in presence of water. Now, the surrounding water is like, say, basic, and you have the same hydrogel, but now it is present in an acidic solution. But the base aqueous medium is there, but one medium is slightly basic, another medium is slightly more acidic. Now you saw that the hydrogel present in the basic solution has swollen lesser in comparison to the one present in acidic solution. So why it has happened? It has happened because some property of hydrogel is there, right? So what is that property? So what type of ions does it attract or has it attracted that led to more swelling in acidic condition?
Negative charge is attracted.
Negative charge is attracted. Okay. So What then? What will the property of the hydrogel then?
Cationic.
Cationic. Are you sure? You sound not very sure. Anyone? You muted yourself. Are you sure? Cationic is the answer here. Think over it.
Anionic.
Hmm? Anionic. Okay, so why do you think it is anionic?
Acid condition.
Anionic hydrogel means it will have much more negative charge, right? Or it will have groups which are negatively charged. Whereas cationic means it will have groups which are positively charged. Now, none of you are saying non-ionic or polyionic. So these two are not in the game. So the hydrogel can either be cationic or anionic. So if it is positively charged, means if it is a cationic hydrogel and you place it in a basic solution where the pH is high. So how will it swell more or will it swell less? What do you think? You have a cationic means positively charged hydrogel and you placed it in a basic solution. The pH is more, like greater than 7. So what do you think? Will it swell less or will it swell more?
More.
More. You're correct. Cationic hydrogens will swell more in basics condition. So what will be the answer here then? Let me check. Oh, answer is cationic, not anionic. How come? It's confusing, right? So the simple logic is, let me just write it down. Anionic hydrogels and cationic hydrogels. These two type of hydrogels are there. People have observed that anionic hydrogels, these are negatively charged, these are positively charged. They will swell more when pH is basic. pH basic means there are more number of hydrogen ions. Correct? That is the definition of pH. I hope I'm not wrong. Right? And cationic hydrogel swells very high. Swelling is high when pH is acidic. Hydrogen ions are less. Let me know if you have understood what I've written. Sorry, I just Googled myself and found that when the pH is acidic, hydrogen ion concentration is the highest, whereas pH when it is, sorry, yeah, more the hydrogen ions, more acidic pH you will get. And in this acidic pH, cationic hydrogels they swell much more. Whereas if uh, lesser the concentration of hydrogen, more the amount of OH, right? OH groups will increase. That will contribute to more basic pH. pH will become more and more basic. And in this higher basic pH, the anionic hydrogels they will swell more. So what the question has asked? The question has asked that this hydrogel has swollen less in basic condition. So and it has swollen more in acidic condition. So what we have just observed from these 2 points, it can only be a cationic hydrogel. Cationic hydrogel will swell more in acidic conditions. It will swell more. Again, I'm repeating. Cationic hydrogels will swell more in acidic conditions, whereas anionic hydrogels will swell more in basic conditions. Got these 2 points? Yes, no? Okay. I got 2 thumbs up, so I'm assuming rest of you have understood. So moving on. So there is beta glycosidic linkage that has formed, and you have to tell me when this beta glycosidic linkage is formed. When the carbon, a C1 carbon, is present in the plane as the ring, glucose ring, when C1 carbon is present above the glucose ring, or when C1 carbon is present below the glucose ring. So phenyl ring is a, it will not come here. Okay, it will phenyl ring. Beta glycosidic linkages are not formed with phenyl ring. So option D is eliminated. So any of these three, A, B, C, is the correct answer. So we just saw beta linkage and alpha linkage. Like I tried to explain them, right? When we talked about the structure of hyaluronic acid. So if you have understood that, I think you can answer this question now. So go back, let me go back to the structure of hyaluronic acid. So here there was beta linkage. The question is asking that only, that when the beta linkage is formed with C1 carbon, when whether it is formed when this particular glucose ring, this is a glucose ring, whether this glucose ring is present above the plane of this, whether it is formed when this glucose ring is present below the plane of this particular glucose ring, or when it is formed when these two are in the same plane. Anyone remember this thing from the lectures? In lecture also, Professor Doble discussed this. Either A, B, or C is the correct answer here.
Yeah, ma'am.
Same plane. No, sorry, that is not the correct answer. A is not the correct answer. Either B or C. Try again.
Seems both B and C. No?
Seems both. Acha. So when will alpha linkage will form? Then either beta या फिर alpha. Either of these two linkages you know of. Okay. That forms between saccharides, monosaccharides. So when will then alpha linkage will form?
In structure, but they were only beta bond, no, ma'am.
Okay, let me tell you the answer. So the answer is B. Correct answer is B. So see, this is the structure. How? So this is two disaccharides given. One is maltose, another is lactose. So alpha glycosidic linkage is formed between C1 carbon of one glucose ring. And here also it is C1 carbon of this first glucose ring. So when we will call the linkage alpha, we will call the linkage alpha when this particular ring, this one, is below, when it is below the plane of this particular ring. So like this, it is like stacked. First alpha D glucose, first alpha D glucose is like this, second alpha D glucose is like this. Then the linkage between carbon 1 of the above plane glucose and the linkage between this is C6, I think, huh? This is C6. So C6 carbon, sixth carbon of second, it will form alpha linkage. Then it will be called alpha linkage. When beta linkage is feasible, when with respect to C1, this is your glucose molecule. It has a C1 carbon. This is your C1, my left hand with my watch. Okay. On top of it, above, the second molecule is present. The above the uh, glucose ring with C1 carbon. Then the linkage that is going to form between the C1 and any other carbon of second molecule, that linkage will be called beta glycosidic linkage. Got it? With imagination, where I able to help you understand. So another simple way is like alpha A, right? Beta B. So B not below. It will not correspond to below. Alpha will not correspond to above. It will be like crisscross. A simple personal thing to remember. Okay, is nothing hard and fast here, means nothing very critical here to understand, just simple memorization will work. Okay, understood? Okay, now here's another question, which does not form a hydrogel. So there are four polymers. I've given the structures of these four polymers to you. Okay, PVP stands for polyvinyl pyrrolidone. HA is hyaluronic acid. PEG, polyethylene glycol. PET is polyethyl terephthalate. Okay, polyethylene terephthalate. So what do you think based on this structure? Which of these could not be a hydrogel, or maybe you have read somewhere that it is not a hydrogel? What do you think? Anyone? Anyone would like to try or give a guess? Maybe give a logical guess. All of them have oxygen groups in them. Sorry, I could not understand what you just said. Can you repeat? Maybe slower this time.
D, ma'am.
D, option D. Okay. Uh, it is correct. Option D is correct. So, did every one of you or all of you who are present here could arrive at option D as the answer, or any other answers you had in mind? Okay. I'm assuming that you guys came to option number D as the answer here. Okay. PEG is very well known to form hydrogel. We use this PEG hydrogel to deliver drugs. Hyaluronic acid is a hydrogel present in our body actually, and we use it widely for various cosmetics and then various biomedical application. PVP is a synthetic polymer. It is not. It is a synthetic polymer like PEG, and it is also a form of hydrogel. Whereas PET is Dacron. It commercial name is Dacron, and we use it in form of plastic bottles. So it is not a hydrogel. Okay, PET bottles you must have heard. So I'll take 5 to 10 minutes to briefly discuss the answers to this to last week's assignment problems. So I'll not take too much time here. So if you have any queries, please stop me in middle. I'll try to explain that part in more detail. So the first question was to calculate the Miller index. So for that you were already given the intercepts, and XYZ intercepts was given to you. You had to take a reciprocal and convert it into integer form. Miller index cannot be in fraction. So when we do that, you will get the answer. So answer was 2 bar 1 4 bar. That was the correct answer. Now, if you look at question number 2, the values of the axes A, B, and C, they were not equal. Also, the angle of alpha and beta was 90 degree, and gamma was not 90 degree, it was around 120. So when you look at these properties and match with the different type of seven, actually four, sorry, 14 types of unit cell, you will find that the monoclinic unit cell matches this description accurately. Other unit cells doesn't match this description. Then in question number 3, we had to simply choose which of these type of unit cell, HCP, FCC, and BCC, is more plastic or less plastic in this case. So if you see the order of plasticity, BCC is highly plastic, whereas HCP is the least plastic one. Okay, so keeping that in mind, we had to choose this option. So this was the correct answer. Then question number 4, you were asked the coordination number of alpha aluminium. So coordination number referred to the number of atoms surrounding, so number of surrounding atoms. So it was a cubic structure. So alpha aluminium has FCC kind of a unit cell structure, and in unit cell, one atom, any one atom you take in that particular unit cell, it will have four surrounding atoms in its plane, four atoms above its plane, and four atoms below. So in this way, for one atom, there will be 12 surrounding atoms. So that is the coordination number that you had to write. Then this for this question number 5, we had already solved this type of problem in last week problem solving session. There we had calculated percentage decrease. Here we had to calculate percentage increase. So first we have to determine the atomic packing factor of BCC structure and FCC structure, which is given, like if you Google it, you can find those values, and using those values you can determine the percentage increase. So what I got 8.8%. Next, for question number 6 and 7, here slight variation. So in last week, I had discussed exactly similar, like very similar to this particular problem. But there, the ball was part of a hip joint prosthesis, means ball was rubbing continuously to a socket. So there we had done the calculation slightly differently, but now it was not written where the ball was placed. So it was just written that the ball was undergoing some wearing process, and because of which cobalt ions was wearing at the rate of whatever 0.1 per year. And from that we have to calculate what is the number of ion released in 2 years. So here's my calculation for it. Uh, Only thing that is different from that particular problem, last week's problem, and this particular assignment problem is you have to consider that the entire ball or the cobalt ions from the entire ball is leaching out because of the wearing process. So accordingly, you have to calculate the volume. And so I have done it. You can see in the screen. And using that volumetric wear rate, you have to calculate the number of cobalt ion released per year. So that is also very similar to the last week's problem. And when you do that, you will get 2.33 in 10 to the power 21 ions will be released in a year. So for 2 years, how many ions will be released? So the correct answer will be 4.66 to 10 to the power 21 ions. Okay. So the answer, if you have gotten around two, if you have gotten answer of around two, you that is actually incorrect. The logic of the question nowhere states that the ball was coming in contact with the socket. So the half of the volume was in complete. Half of the volume was undergoing the wearing process, but the rest half was not. So that is why in this case, we cannot use that logic. The correct answer is 4.66 in 10 to the power 21. So if anyone has any query, let me know. For this question, I'm saying. Have you understood why the answer is 4.66? Okay. Now moving on, answer to question number 8 was polyvinyl alcohol, which was, I think they were asking, let me just read the question. So they were asking which of these polymer is biodegradable. So among all the options given, PVA or polyvinyl alcohol is biodegradable. Then we have to find out which of the polymers does not have oxygen present in it. So if you see the structure of the options of the polymer that are with you, that is PMMA, PVC, PVA, and PC, polycarbonate. Only PVC does not have oxygen present in its structure. Rest all the three types of polymers have oxygen present in it. And then the last question, question number 10. Here you had to calculate the number of repeat units. You are given the number average molecular weight and also the repeat unit structure. So from the structure of the repeat unit, you can calculate its atomic weight, which is coming out to be 14 grams per mole. Use that value, okay? And you can get the number of repeat units. So that's it from my end, okay? If you have any more queries or anything more you want to discuss, because today we have Karthik as well, who is another TA, and maybe he will be able to help you guys more than myself. So if you have any query related to the course, and if any difficulty you are facing in understanding any topic, then maybe I can take it up in the next week, because next week is the last problem solving session on my side, and then there will be exam and also anything you guys want to discuss. Was today's discussion fruitful to you? Okay. Any topic you haven't understood and you want me to consider that or take it up in the next week? I'll prepare for it and help you out. Because I saw the content of week 7. It is, I think, very simple in comparison to what we have been studying so far. So in addition to that content, I can definitely take it up some more difficult content like the mechanical properties. So that part was very big, and many mathematical problems were a bit tricky to solve. So if you guys want me to take it up in a specific topic, you can let me know. Okay. So are there no queries? Have you guys understood the problems that I solved today? Will you be able to solve the assignment problems now will you, by yourself? Or you have any difficulty in understanding any particular assignment problem maybe for this week? Okay, then it was so let me just then wrap up today's session and I'll see you all for the last time next week. Next week will be the last session for this problem solving thing. And then I hope you enjoyed these sessions that I took. If any mistakes I have done, please apologize. Like please uh like get I'm also learning this art of teaching myself. So okay, thank you for joining you all and I'll see you all next week. Bye. You guys can leave the meeting now.